Thanks for the introduction. First of all, I'd like to thank the organizer for giving me the opportunity to speak here. So I'm going to be talking about joint work with Song Sun from Stony Brook about Kähler-Einstein metrics. Any talk about Kähler-Einstein metrics has to start with the Calabi-Yau theorem, famous theorem from the 70s. So that's a statement. If you have a compact Kähler manifold whose first Chern class is 0, then every Kähler class contains a unique Ricci-flat Kähler metric. So even if you're not entirely sure about the definitions of some of these words, what this is telling you is that there exist plenty of examples of compact Ricci-flat Riemannian manifolds that aren't flat. And that was the big feat. That was the big thing with this theorem when it was first proved, because there weren't any other ways at that time, and basically there still aren't any other ways to construct examples of compact Ricci-flat manifolds that aren't already flat, like tori. So for the purposes of this talk, you'll have to understand the statement a little bit better, with a little bit more detail. So I'm going to give an example to show how the theorem is actually applied in practice to get concrete examples. So that's the simplest thing you can do. You get your Kähler manifold X as the zero locus of a homogeneous polynomial of so many variables. And so what you're going to do is you're going to take a homogeneous complex polynomial of degree n plus 2. So n is going to be the dimension of x in as many complex variables. If you choose the polynomial generically, then the vanishing locus of the polynomial in CP n plus 1 is going to be a smooth hypersurface. So that's what the generic does for you. The hypersurface is going to be smooth. And this degree condition, that the degree is equal to the number of variables, implies precisely that the first Chern class of this complex manifold, this Kähler manifold, is 0. So it's very easy to check this Chern class condition. Just the degree, take a polynomial of the right degree. So then Yau's theorem tells us that there exists plenty of Ricci-flat, obviously non-flat because these things are simply connected, metrics on this complex hypersurface. So then Yau actually tells you that you have a degree of freedom there to pick a Kähler class in the second cohomology of your manifold. I don't want to use that whole freedom here. I just want to restrict, so for emphasis, to one particular Kähler class, which sort of incidentally also explains what Kähler class really means. You take your class to be up to scale the first Chern class of the hyperplane line bundle on projective space. So it's one of the, it's a natural generator of H2 of complex projective space. So that's the Kähler class that represents the Fubini-Studi metric. On projective space, you have the Fubini-Studi metric. That's a Kähler metric. It represents exactly this Kähler class. And so then one special case of what Yau's theorem is telling you is that if you start with the Fubini-Studi metric restricted to your hypersurface, there's a way of modifying it by adding on basically the Hessian, the delta bar Hessian of a scalar function, so that the new metric is actually Ricci-flat. And so the story I want to try and tell you today is sort of motivated by one basic question. So here, choosing our polynomial f to be generic, which meant that this hypersurface x is actually smooth, so it's actually a complex manifold. Now it's very interesting to start to think about what happens as the polynomial degenerates. So I can take a one-parameter family of polynomials. Generically, they're going to be all smooth, and then there's sort of a special value of the parameter where the polynomial acquires critical points, meaning that the hypersurface acquires singularities. You have this Kähler class with the restriction of the Fubini-Studi class. You have that for all values of the parameter. It's a very natural problem to ask, what actually happens to Yau's Ricci-flat metrics in this class geometrically as the underlying complex variety, as the underlying polynomial degenerates and acquires singularities. And this is, it's a perfectly reasonable question in this generality, and there is no good answer in any generality. So we're very, very far away from answering this in any useful way. And I can sort of tell you right away, in a very simple example, what the main problem is, why we cannot answer that question. Draw an example. The simplest thing you could take is CP2, and then you would have to take a look at the zero locus of a cubic polynomial, so that's an elliptic curve. So draw a standard picture of the elliptic curve. That's a singular one, so that would be your x0, singular elliptic curve. Then you have a family of smooth ones approximating that singularity. So the red ones here are smooth elliptic curves cut out by the cubic polynomials without critical points, and as t goes to 0, we get this degeneration. This variety acquires a slow singularity. Now, an elliptic curve is actually just the complex numbers modulo some lattice. That's what a smooth elliptic curve is. So I was lying before when I said that Gauss' theorem always produces these non-flat Ricci-flat metrics. So that example of the lowest possible dimension, where you just take the elliptic curve, there the metric is actually flat. Because in that one particular example, these hypersurfaces are not simply connected. Actually, they're just tori. So I don't need Gauss' theorem to construct Ricci-flat metric. It's just a flat metric on an appropriate torus. And then so what happens to that flat metric as the torus degenerates, so if the volume stays fixed, meaning that one direction of the torus goes to infinity and the orthogonal direction of the torus gets collapsed to a point, so you get a Gromov-Hausdorff limit, which is an infinite line. So you have flat metrics degenerating and dropping dimensions. So that's basically a trivial example of collapsing. And so if collapsing is the big enemy in this business, I mean, this is not at all understood in any generality. There's very few tools to deal with that situation. So if we want to have any hope of saying anything reasonable, we have to introduce some sort of extra conditions that rule out collapsing a priori. So that you want to take some limit of these metrics, of these Ricci-flat metrics, and see what happens to them geometrically, but you want to make sure that the limit they're converging to at least has the same dimension. It doesn't drop dimension. So there's a well understood way of doing this that I can't completely explain, but it turns out that the right condition on these varieties that rules out collapsing of the Ricci-flat metrics is to assume that this limiting singular variety has at worst canonical singularity. So I'm not going to try and explain what canonical means, but it's sort of a mildness condition. So if the singularity of this limiting variety is sufficiently mild, then the Ricci-flat metrics don't drop in dimension at least. So that's a basic assumption. And so the simplest singularity here of an elliptic curve with a double point is not a canonical singularity. That is not sufficiently mild in this sense. And in fact, if your complex dimension is 1, so if you're talking about complex curves like this, then there aren't any canonical singularities. If you have a singularity that's canonical, it's actually a smooth point. So that makes some sort of sense. It actually gets a lot more interesting in complex dimension 2. If you look at complex surfaces, then you can show that a singularity of a complex surface is canonical if and only if it's a quotient singularity. So quotient singularity means that so if you take C2, a complex plane, and mod it out by some finite group gamma, finite subgroup of SU2, that acts freely on the unit sphere. So the only fixed point is the origin, so the quotient space is going to have an isolated singularity. And that's a picture of the quotient space, isolated singularity here. And so the link of the singularity, the boundary of a neighborhood, is going to be a spherical space form. It's going to be S3 modded out by that finite group that acts freely. So this is S3 mod gamma. So in particular, because the group acts freely, just said that the singularity is isolated automatically. Of course, there's plenty of non-isolated singularities of complex surfaces. So just for that reason, this canonical condition really cuts down the possibilities of singularities to be that you can see. If you're going to even higher dimensions, there's no useful classification. So for starters, a canonical singularity doesn't have to be isolated. You could have like a higher dimensional singular set. And even if it is isolated, it doesn't, it typically doesn't look like this. It's not a quotient singularity. And actually, in the setting that I've been describing, where you start with a family of smooth guys and you degenerate into something singular, if the dimension is at least 3, if the complex dimension is at least 3, then you'll never see isomorphic orbifold singularities like this if you only talk about canonical singularities. So somehow for higher dimensions, this class of singularities, well, they're still sufficiently mild for this theory to go through, sort of, a lot less well understood. It contains a lot more complicated singularities than just these simple quotients here. So maybe it's not so surprising that the question I asked about what happens to Ricci flat metric is actually completely understood in complex dimension 2, thanks to this result of canonical singularities or quotient singularities. There's a very nice and very complete picture I'm going to describe quickly. So you have these smooth hypersurfaces that acquire singularities in some funny way. Locally here, the singularity of the picture is just a quotient of C2. And so it turns out the right way to go about it is to say, on the smooth hypersurfaces, I do have smooth Ricci flat metrics from Yau's theorem. And it's actually pretty easy to prove an extension of Yau's theorem to the singular case, because these are just orbifold singularities. These are just quotient singularities. So you actually start by constructing a Ricci flat metric on the singular guy, but proving an orbifold version of Yau's theorem. And that's very easy, because if you do analysis, then analysis doesn't care about orbifold singularities. You just pass locally to some finite cover, and then the analysis is exactly the same as in Euclidean space. So that's actually doable here. So you can show that on the singular variety there exists a Ricci flat orbifold.
I think that the first person to actually state this in the literature is probably Suji, but although with more emphasis on the negative case, but the same observation.
Yeah, well, so geometrically, what this means to have a Ricci flat metric with any Riemannian metric with orbifold singularities really is just what I said before. You have a metric on the orbifold, and you pull it back under this local covering map, under this quotient map, and you get something that's smooth. So in particular, it's equal to the flat metric on C2, plus sort of smooth the decaying errors, like in normal coordinates. So geometrically, what this means is that the metric picture here near the singularity, the Ricci flat metric really looks like a flat cone. And once you have this, that's sort of that's the basic ingredient, that you know exactly what the singular Ricci flat metric looks like geometrically, and then you can go about analyzing what happens sort of close to this limit, so very close to where the singularity is forming. So that story is a little bit more complicated, so I'm not going to try and explain that. But basically, I mean, it's understood by now at least that you can describe that in terms of gluing construction. So you have the singularity here, this conical singularity, and there's sort of Ricci flat model spaces that you can glue in. Ricci flat model spaces that are sort of asymptotic to the singularity as you go out to infinity, and then there's enough of these that you can do a gluing construction that recovers all the possible examples. So you can get like a very precise analysis of what the behavior of the metric is, so very shortly before you reach this orbifold singularity. So So you can describe what sort of topology pinches off in the limit, what sort of topology gets sucked into the singularity. And you have very precise information about the metric as well. So that's a beautiful theory that took many years to develop, but now it's essentially complete. Now I'm interested in the higher dimensional case. And as I said before, so the problem with these canonical singularities in higher dimensions is that there is no useful classification, and they're basically never orbifold singularities. And if your singularity is not just the quotient of something smooth, there's no way you can sort of pull this the same trick and prove like a version of Yau's theorem. You can prove something, but it's not anywhere nearly as precise as the picture you have in dimension 2. And in particular, it does not really tell you what the Ricci-flat metric looks like geometrically. You have some random estimates on the metric that sort of blow up in an arbitrary way as you approach the singularity. And people have worked hard to try and get around this difficulty. So I'm going to summarize some of those results. It's just a basic, general structure theory of what these metrics look like, even though it's not nearly as complete as in the two-dimensional case. So the first result is some version of Yau's theorem that says, well, even though I don't know exactly what the singularities are, they can be kind of complicated, there still is some sort of weak solution to the Ricci-flat equation on this singular thing. Some sort of Ricci-flat metric that's incomplete, that acquires some kind of singularity as you go out here. But it's smooth in the interior of the manifold, so it's actually a smooth Ricci-flat metric on the regular part of your variety, except that you don't really have any good estimates on what happens as you approach the singularity. And then so if there's a complementary result that tells you that so if the smooth Ricci-flat metrics omega sub t that live on these smooth varieties, that they actually converge sort of smoothly, uniformly on compact sets. If you excise the neighborhood of the singularity, they converge to this weak solution that you have on the singular variety. And it also tells you that you have Gromov-Hausdorff convergence globally to the metric completion. There's this picture here that I tried to draw in 2 dimensions, that you have these smooth spaces with some topology here, and the diameter of these topological cycles is going to 0, and so it pinches off and creates the singularity. So you do have Gromov-Hausdorff convergence to the singular space, which is the diameter of these cycles, these pieces goes to 0. What you get here is almost the same statement, except that you have to take the completion of this weak Ricci-flat metric that you have in the regular part. And there's sort of a nasty question that arises because we don't understand the singularities at all. Could it be that the singular set of this completion is much bigger than the singular set of the underlying complex variety? So here's your singular variety x naught. Let's say it has only an isolated singularity. As a complex variety, let's say it only has an isolated singularity. But here on the regular part, you have this smooth Ricci-flat metric. It's incomplete as you go out to the singularity, but you don't really have any good estimates on how the metric behaves. So a priori, it could be that if you look at the metric completion of this incomplete metric, it sort of opens up. It creates like a higher dimensional boundary. It could sort of the ideal boundary of the completion could be some sort of higher dimensional set, even though the original complex variety only had an isolated singularity. That's sort of the extent to which these estimates are insufficient, that you can't even rule that sort of behavior out at the singularity. That you get these extra components of the singular set. And it took a long while for people to actually resolve this and to show that the metric completion of this weak Ricci-flat metric is actually homeomorphic to the underlying complex variety that we started with. So this thing can't happen. And the topological picture and the metric picture agree, at least in this sense. So topologically, the completion is homeomorphic to the original variety. But this is deep and difficult work. But then you can try to start building more structure. So now I know what the thing looks like topologically. Can I try to say more about the structure of the metric at these singularities, keeping in mind the fact that they're not orbifold singularities, or there's no obvious guess for what these singularities could be. And there's some structure theory you can use for that now. So it was developed by Kähler and colleagues. So I put a random number there around 2000, and that tells you that these metrics have tangent cones. And somehow you can get this metric here. No idea what it looks like geometrically, except that it closes up on one point. What you can do is you can take rescalings. So you fix your singular point x here, and you multiply the metric by a sequence of scaling factors lambda j that goes to plus infinity. So you zoom off, you dilate down, and Gromov's compactness theorem tells you that you have subsequential Gromov-Hausdorff convergence to some metric space. And then Kähler-Holding theory tells you that whenever you have a sequence like this that does converge in the Gromov-Hausdorff sense, like a sequence of rescalings, then the limit has to be a metric cone. So that's maybe one relation of this talk to the theme of the conference, that this is sort of the shadow of the Toponogoff splitting theorem for non-negative sectional curvature. So the reason that this limit space has this rigidity, that it sort of splits off a radial direction, that's a shadow of the Toponogoff theorem, sort of generalized from non-negative sectional to non-negative Ricci curvature. So the point is the limits are metric cones, and I'm just going to remind you what a metric cone actually is. So metric cone is metric space. It splits as a product like this. So you have some sort of cross-section y. Y is the cross-section. And then, y could be a singular metric space itself. I mean, that's a generic expectation, that y is actually has singularities itself. So y might have singularities here and there, and then the cone over it is going to have rays of singularities. It's not going to be singular only at the apex. It's going to have entire arrays of singularities. And of course, this is the formula you write down for a cone metric in Riemannian geometry. If the diameter of the cross-section is at most pi, there's sort of a nice way of generalizing that formula to just pure metric spaces to get the distance function of the cone in terms of the distance function of the cross-section. But I didn't want to write that down, so this is much easier to understand. It's the same idea. You take the cross-section and you scale it down linearly. It's the cone cross-section y. So then I'm connecting up with Toby's talk yesterday. This is a statement about subsequential limits. So a priori, it could be that if you if you blow up with a different sequence of scaling factors, you converge to some completely different cone. This is like Toby's cylinders yesterday in the mean curvature flow. The singularity model is conical, so it splits off the special direction. But sort of as you go into smaller and smaller scales, you might see one cone infinitely many times and a completely different cone infinitely many times also. And that's sort of one of the basic questions in geometric analysis to deal with that kind of issues of the uniqueness of asymptotic limits. So this is not solved in any great generality. So it's a fundamentally difficult problem. It's exactly like these rotating cylinders in the mean curvature to rule out that possibility. It looks like a cylinder, but the axis of the cylinder might be rotating, and as the cylinder gets smaller and smaller, it disappears in the singularity. The expectation is that no, obviously, but that's sort of fantastically difficult. And that's a really hard problem. So there's a great result from Donaldson and Sun, posted last year, that says that for these Kähler-Einstein metrics, we always do have uniqueness of tangent cones. There's sort of a long story I could tell you about the history of results like this. So for minimal surface, what Toby mentioned, for minimal surfaces, you have Allard and Almgren in the case that the cross-section is smooth and the cone is what's called Jacobi integrable. Then you have Lee and Simon that applies when the cross-section is smooth, but without assuming that the cone is Jacobi integrable. Then you have Bill and Toby's work, getting rid of that assumption that the cross-section is smooth, and in some cases, for minimal surfaces in curvature flow, there's a dual version of that whole story for Einstein manifolds or for Ricci flat manifolds. So Alan Armgren corresponds to Chigartian, smooth cross-section integrable cones, and smooth cross-section non-integrable cones. So the Lee and Simon version was also done by Bill and Toby fairly recently. But the magical thing is that for these Kähler-Einstein manifolds, it is actually possible to prove uniqueness of tangent cones completely unconditional. And that's a great thing in that paper. So what that means is that the singular metric that you have is really asymptotic as you go out to the singularity to one particular definite cone. It's like a derivative, like the first order approximation at the singularity in some Gromov-Hausdorff sense, or converges to that cone in a Gromov-Hausdorff sense. And this really uses very special properties of the algebraic set. You have all this underlying algebraic structure floating around that allows you to do things that would be completely impossible if you're thinking about mean curvature flow or Einstein manifolds that are not Kähler. So for example, what you have to use is that on a cone, you have harmonic functions that grow at a polynomial rate. If your cone is Kähler, comes from a Kähler manifold, then you also have holomorphic functions that grow at a polynomial rate. So generalizing spherical harmonics on Rn or on Cn. So you have an analog of that on every cone. And the remarkable thing is that on a Kähler cone, the possible growth rates of holomorphic functions are a priori known to be algebraic numbers. So they lie in Q bar. And Q bar is a totally disconnected set. So even if you have two different tangent cones and you would sort of be oscillating between two different tangent cones and two infinite sequences of scales, you would have to be sort of moving continuously from one tangent cone to the other. But these growth rates of holomorphic functions, being algebraic numbers, can't move, they have to stay fixed. Particularly the dimension of the space of holomorphic functions of a particular growth rate has to stay the same even as you pass between different tangent cones. So that poses some very strong rigidity that you don't have at all if you're thinking about mean curvature flow or anything that comes from the algebraic structure. So then the big open question left open after these results is, can you actually calculate what the tangent cone is going to be? You have your singular variety that's given by some completely explicit polynomial. This theory tells you that there is a unique tangent cone for these singular Ricci flat metrics. Can you actually tell what the tangent cone is? Can you calculate it concretely? There's just some work that I did with Aaron Neighbor a couple years back that shows that these, when the question isn't as straightforward as you might think if you just start thinking about it. So what can happen? So unfortunately, we were only able to make local examples. So examples of Ricci flat metrics that are defined in some neighbor of the singularity, but that don't connect up to some compact variety in an interesting way. So it's much less obstructed problem just to construct local examples. What happens in these local examples is that so the underlying complex variety has an isolated singularity, so then there's some sort of weak Ricci flat metric here. But as you zoom out to pass to the tangent cone, you sort of magnify this picture. Start off with something that has an isolated singularity, but as you zoom out and pass to the tangent cone, you have sort of topology pinching off, and the limit is actually more singular than the thing you started with. So the tangent cone is going to have rays of singularity actually. So here's singularity isolated. Now you have a whole array of singularities, or a line even. And the reason for this is that there's some topological cycles in here that get sort of squeezed off and disappear completely. it means that if you start out with some complex variety and you're trying to guess what the metric tangent cone of the Ricci flat metric is going to be, you cannot assume that there's homeomorphism stability. I mean, you cannot assume that the cross-section of the tangent cone is even going to be homeomorphic to the cross-section of the original singularity, because here the cross-section of the original singularity is a smooth manifold because that's an isolated point, and here you're converging to something more singular. It's actually a suspension of a smooth manifold. Metric suspension. So the point is that in this work, in this theorem that I'm going to present, we've been able to rule this out. In certain cases, and actually we were actually able to determine the tangent cone explicitly, so in terms of computable data, so that we know exactly what that metric is asymptotic to and in which way. So the first thing is that, again, so this class of singularities that we're considering, these canonical singularities, in dimension 3 and up is sort of extremely general. It contains lots and lots of strange singularities that have no easy description. So, and we're certainly not covering all of them. I mean, far from it. So what we do is we isolate a subclass of these singularities versus some good hope a priori to be able to pin down the metric tangent cones. I want to describe the class of singularities. So that takes some work, unfortunately. Some notation at least. Start with something compact. So you start with CPN. N is the same as before. And inside there, you pick a smooth hypersurface of not too large degree. So the X-versus condition means that the hypersurface is Fano, which means that you can hope for there to exist Kähler-Einstein metrics with positive Einstein constant on the hypersurface, but you can ignore that condition for now. With some smooth, compact, complex submanifold of CPN. So this is C. And now I want to use that thing to build an example of a singularity in one dimension higher. So Z is going to have dimension n-1, and I want to build an example of an n-dimensional singularity from that. And what I can do is I can take a complex cone. So CPN is the hyperplane at infinity of affine n+1 space. If you want Cn+1, f on n+1 space, here's the origin, and rays through the origin in Cn+1 correspond to points on the hyperplane at infinity. Standard picture. So now what I can do is I can take this complex hypersurface inside CPN at infinity and cone it off. Just take the points of Z and connect them to the origin in Cn+1. And this way I'm going to get an n-dimensional variety, so I've increased the dimension by 1, but it's going to have the singularity at the origin that sort of reflects exactly how complicated Z was to begin with. And then I cone it off. And that thing is complex affine cone. These are complex lines to the origin, so I'm increasing the complex dimension by 1. And now it turns out, so this is an observation, so it's a very influential observation that goes back to Jean Calabi's work in 1979, that if you assume that there's a Kähler-Einstein metric on this hypersurface, so there's some metric whose Ricci is equal to +1 times the metric, then you can sort of lift that and extend that to the cone and make a Ricci flat metric on the cone, which is actually a metric cone. So it has this dilation symmetry. It can be written in this form, the r² + r² times something on the cross section. Here you have omega z, this is Einstein. Then Calabi tells, so you assume that you have something like this, then Calabi tells you how to get a Ricci flat cone metric on this affine cone. So on here you get omega star Ricci flat. So that's a class of singularities of algebraic varieties, these affine cones, that comes with a natural Ricci flat cone metric by construction. So you have an underlying variety, that's this guy, but by construction there's this canonical metric on there, which is Ricci flat Kähler, and has this conical symmetry. So that's a class of candidate manifolds candidate singularities that people have been wondering about for a long time. I mean, that's sort of the only thing you can imagine, that if you have a complex variety with singularities that look like this locally, then because you have these nice metric models of Ricci flat Kähler cones on there, it's just the only thing you can think of that this is going to be the tangent cone of whatever, Einstein metric you have on your variety. So it's singularities together with natural cone metrics. Maybe we give sort of the simplest example of this construction, be a little bit more concrete. You could take Z to be the simplest non-trivial variety in CPN. So you would just want to write down into a smooth hypersurface. The simplest thing you can do is take a smooth quadratic. So Z1 through Zn plus 1 here are homogeneous coordinates on CPN. Homogeneous polynomial, so that cuts out the complex hypersurface, the simplest one you could think of. And then this construction here, in terms of coordinates, it's really trivial. You take your homogeneous coordinates, Z1 through Zn plus 1 on CPN, and you view them as affine coordinates on affine n plus 1 space. And then, this cone here is just cut out by the same equation. Because your polynomial was homogeneous, the equation is invariant up to scalars, if you dilate coordinates, and that's exactly these rays that you see here. So the invariance of this affine equation under this homogeneity, its invariance under dilation. So that's pretty easy. And in this case, it's actually possible to write down this Calabi metric omega star completely explicitly. You don't have to pick any transcendental data. There's a lot of symmetry here because SON plus 1 is acting on this setup. SON plus 1 is exactly the Lie group that preserves this quadratic form. So there's a lot of symmetry, so you can write everything down explicitly. And it turns out that this metric omega star that we're going to use as a model is just delta bar of some very explicit potential. So mod z is just the Euclidean radius in Cn plus 1, so you have to raise that to a slightly different power. So if you ignore that power here, delta bar of mod z squared is the Euclidean metric. It's just Hessian of the distance function squared. So what that means is that if I take the Euclidean metric and restrict it to that cone, it's not going to be Ricci flat. But what I have to do in order to get the Ricci flat metric on the cone is to raise the distance function to a different power to sort of correct that. That makes the metric Ricci flat. And these things are actually metric cones in the sense that I described before. So you have this affine, this complex cone is actually a real cone, or some real manifold of real codimension one, and then you have a circle fibration that goes. You have a cone, and you mod out by real scalars. You get the cross section of the cone, that's y, and then you want to mod out by complex scalars to get sort of the complex cross section z. And the way you do that is that you, in addition to modding out by real scalars, you also mod out by the angular direction by unit complex numbers. So this is this S1 fibration here. So this is what these things look like. Now you should go back to the case when n is 2. So when I said that everything is completely understood. So if z is just conic section quadratic curve in CP2, And this affine cone is just one of these quotient singularities I introduced before, Z2 or Z2. And this real cross-section of the cone, which has, so Z is real is complex one-dimensional, real two-dimensional, then that thing here has to be real three-dimensional because the cone itself is real dimension 4. That's actually the unit tangent bundle of S2, in other words, it's RP3, so it's a spherical space form. That's the cross-section of the singularity in this case. But reiterating this point from before, if the dimension is at least 3, so the picture changes completely and the thing is not a spherical space form anymore. So this is not just a quotient singularity. It's entirely new kind of singularity. And then so here's our main result. It's not stated in the most general form. I'm just recalling some notation. So the dimension is at least 3. You look at this family of complex hypersurfaces cut off by polynomials f sub t. You assume they're smooth. So it's degree n plus 1 hypersurface in n plus 1. So this is what makes it Calabi-Yau. This is what makes the first term plus 0. You assume that when the parameter reaches 0, that the variety acquires a singularity. We do want to assume that that this variety has adverse isolated canonical singularities. Then you get this weak Ricci-flat Kähler metric that you expect is your Gromov-Hausdorff limit. And I also want to assume that each singularity of the variety is actually algebraically isomorphic to one of these models. So all of the singularities are isolated, and each of them has a neighborhood that's actually algebraically isomorphic or biomorphic to one of these model cones that I introduced here. But the cross section, you can have a different cross section at each singularity. That's allowed. So you have finitely many singular points, and at each point you have a local model like this, but it could be a different Z at each singular point. That doesn't make any difference. And then you have omega star, these Ricci-flat model metrics. And then the theorem is that locally near each of these singularities, the Ricci-flat metric, this weak Ricci-flat metric that we a priori knew nothing about, and we developed all this big machinery to sort of describe what it looks like, that this is actually asymptotic to these concrete models. I mean, we knew that there had to be a unique tangent cone from Donaldson's son and all the preceding theory here holding. We had no idea a priori what that tangent cone was. And now the theorem says that under these assumptions, the tangent cone is exactly the model cone that we were hoping it would be. You couldn't really imagine at the outset that it would be anything else. But yes, you get more. You don't just get that the tangent cone is this model cone that you wanted it to be, but you actually get that there's polynomial convergence. So there's a biholomorphic map relating the variety to the model. So if you pull back your singular Ricci-flat metric under this biholomorphism, it's actually going to be asymptotic to this conical model metric at a definite polynomial rate. So if you put k equals 0, so if you're not measuring any derivatives, then it's just saying that the difference of the two metrics measured with respect to any one of them goes to 0 at the polynomial rate as you approach the singularity. So this actually solves a problem that has been open for a long time, and people have been wondering about this for many years, at least since the early 90s. So these are the first known examples of compact Ricci-flat manifolds that have actual singularities, isolated conical singularities, but the cones are not flat. They're not just quotient singularities. It's maybe not immediately obvious why people might care about such things, but there's been understandings of the community for many years that if you're actually able to construct singular Ricci-flat metrics like this, you could use them as a basis for all sorts of Wooing constructions. So there's proposals for constructing special Lagrangians, for understanding the behavior of special Lagrangians if you're able to construct singular Ricci-flat metrics of this kind. There's proposals for constructing G2 manifolds if you start with a Calabi-Yau threefold with these singularities. There's a proposal for going up one dimension and constructing G2 manifolds with various interesting properties. So that sort of opens the door to all kinds of gluing constructions that people have been proposing that you hopefully are now able to do once this existence theorem has been proved for singularity. So one thing is that so the simplest example I described where this hypersurface C was just a quadric. And this is the case that people mostly talk about. It's the case that physicists like to talk about because the metric in this case is so simple you can write it down completely explicitly. But we're not actually using any special properties of this explicit model. I mean, this is what I say the theorem in greater generality. And again, this has a lot of symmetries. We're actually able to write down the metric explicitly because of the SON+1 action on here. But so that sort of symmetry that you have, that doesn't play any role in our proof. I mean, it's more of an obstruction than something that would help you. So actually, the less symmetry your cones have, the easier the proof gets in many ways. And you can very easily write down examples of other cones that occur here that are admissible, that are not of this explicit type. So you just take exactly the same construction that I wrote down here, take the lowest interesting dimension, n equals 3, but don't take Z to be a quadric like this, just take a cubic. So raise all the coordinates to a power of 3 in the lowest dimension. Any smooth cubic surface is Kähler-Einstein. So Calabi gives you a Ricci flat model cone metric. The theorem works with its cubic singularities just as well as with the standard quadratic ones, except that in this case the model metric is not explicit at all. It's highly transcendental. Nobody knows what it looks like, and it has no killing field. It has no continuous isometries, and generically it doesn't even have discrete isometries either. And that, in a way, only makes the existence proof easier. So then I have two remarks for specialists. So the first one is that I said, we don't just pin down the tangent cone of these metrics, we even prove polynomial convergence towards the tangent cone. If you've worked on tangent cones, you know that you don't usually get that unless you do assume that the cone is Jacobi integrable. The sort of a la Roundgren for minimal surfaces and Tigert-Tian for Einstein manifolds. If the cone is Jacobi integrable, you do get polynomial convergence. If it's not Jacobi integral, whatever that means, you expect much lower convergence, sort of logarithmic convergence. And that's sort of the generic behavior you expect. I mean, polynomial convergence is a very non-generic thing. So for specialists, this might be slightly surprising. I might be able to say something about this later, but one interesting point is that this, I mean, it's nice that we have that, but there's sort of more to it. I mean, it's not just a bonus, you know, knowing what the tangent cone is, and then you get this extra information that actually converges. The way the argument is, you know, constructed, we wouldn't actually be able to close the argument, to complete the bootstrap, if the cone was converging logarithmically. So there could be some sort of evil twin universe where the same theorem is true, the tangent cone is what I would like it to be, but the convergence is much worse than polynomials, only logarithmic. That's what you would expect at first sight. But if such things actually existed, we couldn't prove that they exist. So this is sort of a flaw of the method. We cannot nail down the tangent cone without automatically at the same time proving that it converges polynomially. And no, luckily for us, it isn't always true. So that's why we're able to prove it. So the last remark I'm going to make also for experts of this, the setting I described, that you start with a projective hypersurface and let that degenerate, and that you construct your models based on projective hypersurfaces and coning them off. This was just to avoid technicalities in the statement. This was just to fix ideas. Everything goes through, if you use the right language, if you take like a flat family of polarized Calabi-Yau manifolds, blah, 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 and Z is like anti-canonically embedded, or pluri-anti-canonically embedded Fano manifold. So Hilbert surfaces are the simplest cases, and I think that's going to be sort of the main source of concrete examples anyway. Still have a little bit of time to talk about the proofs, how do we actually prove this. And the idea is very simple. It's to set up a continuity method. So now I'm going to be working exclusively on the singular variety, x0, and on there's the regular part, the complement of the singularities. And on there you have omega 0, that's sort of your singular Ricci-Flat metric. But at this stage, so we're just about to prove the theorem, we don't know anything about the singularities except, I mean, there is a unique tangent cone, but we have no idea what that cone actually is. And then we set up a one-parameter family. So at the other end, we have omega 1. That's going to be a metric that has exactly the kind of singularities that you would expect, that is exactly asymptotic to these concrete models. So in particular, it's Ricci-Flat near the singularities, but we don't know if that extends inward globally in any useful way. So what we do is we put these Ricci-Flat model metrics near the singularities, and we just use a cutoff function. We just put some random metric in the interior to make it global. So omega 1 is constructed by brute force. It's some sort of initial metric to start the continuity method equal to the model, and it's precisely Ricci-Flat and conic in each singularity. But in the interior, we have no idea what we should do there. And so omega 0 is exactly the opposite. It's Ricci-Flat everywhere. It's good everywhere. We just have no idea what it actually looks like at the singularities, and then we sort of want to interpolate continuously between the two. That's good asymptotics. It's not globally Ricci-Flat. And the way Yau's theorem is proved is by solving complex Morgan-Ampere equations. So what we do is we write down a one-parameter family of complex Morgan-Ampere equations, so that at time 0, the right-hand side is exactly what it has to be, so that the solution is Ricci-Flat, because we know it's going to be Ricci-Flat. And at time 1, the right-hand side is, well, we constructed this guy explicitly, more or less. So applying the Morgan-Ampere operator is going to give us some function f1, that's what we take at time 1, and then we just interpolate linearly between the two right-hand sides, so we get a family of equations in this way. So one useful property, it's very easy to see from the way we set it up, is that to get this path of metrics, as s goes from 1 to 0, they're becoming more and more Ricci-Flat, and they're staying Ricci-Flat on a definite neighborhood of each singularity. So at time 1, you have some non-Ricci flatness, you have some non-zero Ricci curvature somewhere, but that can't sort of move out to the singularity and then go back again. So there's a definite neighborhood of each singularity that does stay Ricci flat along the whole path, but then at time 0, it's Ricci flat everywhere. Anyway, so then you only have to prove that the set of all parameters where the solution actually does have nice asymptotics, it's sort of asymptotic to the cone you would like to be asymptotic to, that this is open and closed in 0, 1. I mean, you don't have to worry about these equations being solvable. There's this theory of weak solutions that tell you there is a unique weak solution for every s. It just tells you nothing about what it actually looks like. And then you sort of solve the equation again in some sense, but now you want to solve it with prescribed asymptotics. It's exactly this kind of thing. You know that the weak solution exists, and you want to prove sort of higher regularity. You want to show that it's actually at all times asymptotic to a particular hope. So I can't really say anything sensible about the two steps of the proof, except that both are somewhat difficult. Even the openness, I mean, usually the openness in these problems is not a big deal, because that comes from the implicit function theorem. You have your one parameter family of equations, You want to show openness of the set of parameters where it's solvable, so you linearize the equation at the parameter, you study the linearization, which in this case is just a Laplacian. You want to preserve good asymptotics, so you assume at time S0 you do have good asymptotics, and then you want to show for all nearby times the good asymptotics are preserved. So you want to solve your Laplace equation in some way the function space, and so preserve the asymptotics. That's sort of reasonably well known, at least in certain circles, how you do that. But then there's a tricky point here. Inverting the Laplacian gives you the Kähler potential of the solution, but you're interested in the Kähler metric itself. And the Kähler metric is del bar of the Kähler potential, so the operator that you have to prove boundedness for is not Laplacian inverse, it's not the Green's function. It's sort of this kind of Riesz potential where you take two derivatives of the Green's function, you get some sort of singular integral. That's the thing you have to show as a bounded operator to do your implicit function theorem. And on a generic cone, on a completely random cone, that would be horribly false. And then there wouldn't be anything you can do. So one theorem we proved is that I don't have time to explain what the theorem is actually saying, but on Ricci-flat Kähler cones have a special cancellation property that tells you that this is not an obstruction, so this operator is actually always bounded. A priori there are obstructions to this boundedness, but you can sort of check that on a Ricci-flat Kähler cone they always do vanish. And basically what this is saying is that you're asymptotic to this model cone at time 1 by construction. And then if you want to have openness in the continuity method, if you want to be able to deform for, to go from time 1 to time 1 minus epsilon, you might have to move your cone model slightly by a complex automorphism of the variety. That's the upshot. So if you insist on the metric tensors being asymptotic, if you insist that your metric is asymptotic as a tensor field to this model cone metric, then you might not get openness in the continuity method. You have to allow for the possibility that the model cone metric moves sort of along a path to automorphism of the underlying variety. If you account for that, you do get openness, but there are no other obstructions. And that's a special property of the Ricci-flat Kähler cones and generic cone. Given a Kähler cone that's not Ricci-flat, that will be horribly false, and then everything would be stuck at this point. No time to say anything about the closedness, so that uses all of these recent advances of Donaldson and so from the last couple of years. So it's very complicated. I guess we'll stop here.
So I guess there's a related story when you're in the C1 negative case, but it'd be much easier because of the...
I mean, we didn't write it up for C1 negative, but it doesn't actually get easier because the singularities, I mean, if you take a Kähler-Einstein metric with a fixed Einstein constant, then the singularities that you get by blowing up because you fixed the Einstein constant previously are always going to be Ricci-flat. So you'll always be looking at Ricci-flat cones, no matter if you start with something with positive 0 or negative Einstein constant. So the real problem is that you reduce the problem to studying Ricci-flat cones, but the cross-section of a Ricci-flat cone is always a positive Einstein manifold. And this is what you sort of see in the closedness part of the proof. So all the difficulties of the positive Kähler-Einstein problem are embedded into the closedness part of the proof, exactly because the cross-section of the Calabi-Yau cone is always found.
So I had incorrectly guessed that the openness part would be just as hard, but the closedness would be easier than in the negative.
It's exactly the same.
I see.
And also in the positive case, if you do assume that there is a weak positive Kähler-Einstein metric, I mean, that's equivalent to some kind of stability, we know that now, but then proving that has sort of the desired asymptotics is exactly as difficult as the Ricci-flat or in the negative Ricci case. Yes.
Well, the product of S2 and S3 has a homogeneous Einstein-Calabi structure, so to have a Calabi-Yau cone.
Yes.
Construct with an observation theory, singularities of this type.
Yes, that's exactly what I was talking about, this example of the quadric singularity. So if you start with the quadric guy, and now you take n equals 3, then this guy here, the complex, so you get the quadric surface in Cp3. The complex cone over this is going to be an affine complex cone in C4, and that's exactly the cone you're talking about. That's sort of the simplest example to which the theory applies.
Further questions? So let's say thanks for your